So far our declarations had no scope, meaning that once something is declared, it continues to be available. In this section we show how to use blocks for limiting the scope of declarations. A block consists of a declaration and the command in which it has effect. This is called the scope of the declaration. In the example program there are two blocks. The outermost one starts with a declaration of the variable y. The innermost one starts with a declaration of the variable x. In the last command, the x referred to is the one that was initialized to 1, rather than the one that was initialized to 2. To take care of scopes, we introduce two new actions in program graphs, one for entering the scope and one for exiting the scope. For our example program, this gives rise to the following program graph. For readability, we have drawn entering and exiting of scopes as horizontal edges. It is a modeling of scopes that requires us to change our memory model. So instead of having a memory that maps variables to values, we are going to have a memory that is a stack of frames, where each frame maps variables to values. Let us recall the program graph from before, and let us show how the memory evolves as we trace through the program graph. We start at the initial node with a memory consisting of just one frame where x has a value 0. Entering a new scope and declaring the variable y produces a memory at Q1 that has two frames. The one at the bottom is as before. The one at the top contains a variable y with value 0. Assigning 1 to both x and y produces a memory at Q2, where changes have happened in both frames. Entering a new scope and declaring the variable x produces a memory at Q3 with 3 frames, and both the one at the bottom and the one at the top contains an entry for x. Assigning 2 to x and updating y produces a memory at Q4, where changes have happened in the two topmost frames, and note that the value of x used is the one from the topmost frame. Leaving the scope produces a memory at Q5, where only the 2 frames at the bottom are retained. Updating the variable x produces a memory at Q6, where the frame at the bottom has been updated. Exiting the scope produces a memory at the final node where x has a final value of 4, rather than the 5 obtained if scopes had not been modeled. We have now presented the basic ideas and now need to be precise about the details. The memory will be a stack of frames, modeled here as a list of frames. Each frame maps variables and array entries into values. This is a partial mapping because not every variable and every array entry has a value in each frame. The semantics of actions then is a partial function from memories to memories, as was the case before. In order to access values of variables, we need to search from the top of the stack of frames down towards the bottom, until we find the first occurrence of the variable we are looking for. This will provide the value of the variable. If we reach the bottom, the lookup operation is undefined. Similarly, when updating a variable, we need to search from the top of the stack of frames down towards the bottom, until we find the first occurrence of the variable we are looking for. Then we update the value in that particular frame. If we reach the bottom, the lookup operation is undefined. We are now ready to define the semantics of selected actions. For assignment, we compute the value of the arithmetic expression, assuming that we have adapted the semantic function to the new memory model, and then use our new update operation to perform the update. Similarly, for Boolean expressions, the function is undefined unless the Boolean condition evaluates to true, assuming again that we have adapted our semantic function to the new memory model. Note how the declaration of variables differs from an assignment in that an entry is created in the top frame. For entering a block, we simply push a new frame on top of the stack. For accessing a block, we simply pop the topmost frame from the stack. While the online system focuses on procedures, it is possible to use either of the two procedure environments to experiment a bit with the semantics of blocks. When doing so, one should pay attention to where frames are pushed and popped. It will be a good idea to try our simple example programs and scrutinize the execution steps performed. So far we only focused on variables, so now we have to deal with arrays. Again, we need notation for locating the appropriate value of an array entry on the stack of frames. And we need a notation for updating an array entry at the appropriate location of a stack of frames. All of this is taking place by searching from the top of the stack of frames. This is how to adapt the assignment to an array entry to our new memory model. Observe how it differs from the declaration of an array, where new entries are added to the topmost frame. It is time to experiment a bit more with the online system. Consider the following version of the Fibonacci program, and use the system to construct a complete execution sequence from an initial memory where x is 4. Explain why the stack of frames evolves as displayed. Now consider the following array program and assume that you have an initial memory consisting of a single frame that has entries for arrays A0 up to A4. Trace the execution sequence obtained for this program. Consider whether or not this is the result you would have expected. Having done this, you should read the text in the book, doing the try-it outs on the way.